All right, so we still had one more left in the 2.5 section. This is number 4. This is a solar photovoltaic arrays. Essentially, it's these cells in alignment. So you have to pass either 1, 2, or 3, 4 to complete your circuit. So it says there are two subsystems connected in parallel, each one containing two cells. In order for the system to function, at least one of the two parallel subsystems must work. So either we have to go path 1, path 2 to connect it, or we have to go path 3, path 4. Within each subsystem, the two cells are connected in series, so a subsystem will work only if all the cells in the subsystem works. Consider a particular lifetime value t sub 0 and suppose that we want to determine the probability that the lifetime will exceed t sub 0. Let a sub I denote the event that a lifetime cell, either 1, 2, 3, or 4, it will exceed that t sub 0. We'll assume that the a sub i's are all independent. That's important. That means that whether any cell lasts longer than that or not has no bearing on if any other cell does. That helps us because anytime we're doing an intersection, then we can multiply the two individual probabilities together. And this is the original probability P of a sub I equals 0.6 for every I, since the cells are identical. Okay, now they're saying using this, probability that the system lifetime exceeds T sub 0 is easily seen to be 0.594. Now it's 0.4. So maybe that's easy to see or not, but let's write out what it means. So first thing I want to write out is that they told us in just a minute to use this as a hint. So I'm going to go ahead and write this down. But we said for this system to work, we either have to go, so our probability of the system living and working the way it's supposed to, we either have to go path A1 intersect A2, those are those two cells, or our system could work if A3 intersect A4 is still effective. Okay, now that's a union, so we know that there's a formula for union. It's the probability of each individual event, which is these parentheses parts. So either path 1 that we're going down, sorry, that's supposed to be a 2, or path 2, which is the 3, 4. Remember, because this is a union, we need to subtract for any intersection between the two subgroups. So A1 intersect A2 intersected with A3 intersect A4. In other words, all the paths are live and working. So this right here, the reason they kind of, make you think, oh, that's easy. If you put in the 0.6 that we were currently given, this is the probability of A1 times the probability of A2, which they both have the same probability. Remember, intersection, if they're independent, you just multiply the two probabilities together. That's only if they're independent. And then this is just four things being intersected together. So that's going to be 0.6 to the fourth. So I wanted to show you where they came up with that 0.5904 before we solve the problem, because it may not be easily seen to everybody. So 0.6 times 0.6 is 0.36. We have two of those added together, that's 0.72. But then we subtract the 0.6 to the fourth, and that's where you get the 0.5904. So this is where they came up with that magical number. It's from the formula, okay? Now they want us to play a little game for a minute. They're saying, okay, what would we need the probability to change to be in order? So we want to make that 0.6 probability of success. We want it to change in a way that it will increase the system's time reliability from this 59% that it currently sits at to up to 63%. So they're going to tell us to replace all the probabilities of each cell essentially being working and living that lifetime that it's supposed to live by equal to P instead of equal to 0.6. Okay. Now, like I said, because these are independent, essentially, I didn't show it up there and above, I just wrote it. That means each of these intersections, we can multiply the probabilities together since it's independent. This one would end up just being all four of them multiplied together. Times PA3 times PA4. Okay, so if we put in the letter P instead of 0.6, we're going to get P times P, which is P squared, plus P squared, minus this would be P to the fourth. And we're wanting this new probability not to be equal to 0.5904, but to 0.63, okay? That's what they want it to increase to. Now, remember this little extra part of the hint. They said, now we don't want to deal with a bunch of fourth powers when we're solving. Let's do a substitution. Now, we'll have to back substitute at the end. But they said, let's change all the p squareds to x. And the reason that's helpful is because then this is x plus an x, and then this would be x squared since there's two p squareds times each other. So this is a quadratic equation, essentially. Now I would reorder this and add the x squared to the other side, subtract the two 1x's over, so that's going to be minus 2x plus 0.63 equal to 0. We're going to need to use the quadratic formula on this because that's not going to be factorable. Now you could get rid of the decimals if you want, or you can work with them. It's not a big deal. This would be my A, B, and my C. So for quadratic formula, that is x equals negative b, so that's already negative, so that's going to be 2, plus or minus square root b squared minus 4ac. Make sure you don't leave out that decimal point since we didn't clear it, all over 2a. If I work out the inside of that radical on my calculator, that would be 4 minus 4 times 0.63. So that's going to be a 1.48 underneath the radical. So we'll still need to take the square root of that. And I'm going to write this out to 6 decimals since they want my final answer to 4, because that's not going to come out to a nice answer. So this is going to be 2 plus or minus, and I get 1.21. 6553. That's the 6 decimal places, all over 2. Now we know that's going to give us 2 separate answers, an x1 and an x2. So I'm kind of going to break this up over here. So I'm going to use my calculator, and I usually do the minus case first. So 2 minus 1.216553 divided by 2. I'm going to write all of this out because I'm not rounding until the very end. That's 0.3917. 235. Now I did have to round the quadratic formula part because otherwise that would have gotten a little tedious, but I'm not going to round off to 4 decimal places until the end. And then we need to do the plus case. So 2 plus 1.216553 and then divided by 2, that's going to be 1.6082765. Now, these are for x. We wanted to solve for the p-value, the probability that they last that t sub 0 lifetime, longer than that. So we need to go back and think about what p represented. So x was p squared. So each of these can be set equal to p squared. And then we need to take the square root of them to get p. Now, obviously, maybe one of these might fail because otherwise it would be weird to have 2 answers that work for probability like this. So let's do the small one first. So 0.3917235. If I take the square root of that, I'm going to go to 4 decimal places now. 0. And it is 6259. For the other one, if we take the square root of that, so let me type it in. 1.6082765 on my calculator and then take the square root. Okay, this one's the problem. This comes out to 1.268, and I think it was a 7, but let me double check. No, 86. This is not a viable answer because probability should always be less than 1. It can't, remember, all of your probability of an entire universe adds up to 1, but a singular probability should never be greater than 1. So this will be the answer. So they need to have that probability that it lasts, that t sub 0 lifetime needs to be increased from 0.6 to 0.6259. Okay, that is the end of the 2.5 video help.